In this video, we want to introduce an idea known as implicit differentiation, and we'll start with an example. Let's take x squared plus y squared equals 25, and we want to know what is the slope of the tangent line at a single point, in this case 3, 4, but it could be any point on that curve. Well, you may recognize that this curve is a circle, which is new because up till now, we've been doing derivatives only on functions, and the circle is not a function. We know the circle is not a function because it doesn't pass the vertical line test. So here's our circle, and we are interested in the slope of the tangent line there at 3, 4, which is essentially the derivative at that point. So there's our tangent line. It might look something like that. I just estimated it there. Well, first we'll discuss the old way of doing this, pretending we don't have implicit differentiation, and then we can compare that with implicit differentiation, which we'll use from here on out. So the old way might be to say, okay, we have to solve for y first, so we'll do y equals the square root of 25 minus x squared. Now you may say, why not plus or minus? Well, we only need the plus case because we're in the upper quadrants here, so it's only going to be the positive case. Okay, well then we could take the derivative using the chain rule. Y prime equals, all right, so first off, I'm going to write this as 25 minus x squared to the 1/2. Okay, and this is just for demonstration purposes, right? This is not even the point. I just want to show the old way of doing it. So we'd take 1/2, stuff inside stays the same, to the negative 1/2 times the derivative of the inside, negative 2x. That's the chain rule, which we then rewrite as, well, it looks like our 2's cancel there, so we have negative 1 over the square root of 25 minus x squared. Let's see, I just noticed I'm missing an x in there, so all right, let's keep that x in there. Okay, so there's the derivative that way, which we could then evaluate at 3, 4 to get, what would that come to? So we have negative 3 over square root of 25 minus 9 is 16, so negative 3/4. Okay, so we know the slope of this tangent line is negative 3/4. But let's do it another way, which we'll call implicit differentiation. And what's better about the new way is that it won't require us to solve for y, right? Because much of the time, solving for y in equations like this is going to be challenging, if not completely impossible. We'll see equations very quickly where you can't solve for y. It's so entangled with x's and trigonometric functions and all that, there's no way to get y by itself, so you have to use implicit differentiation. So here's how that goes. Okay, we'll call this the new way, implicit differentiation. Now, we already know when we solved this equation for y, we got y as a function of x. So that's the important thing to note here, is that y is a function of x. So anytime you see y, remember y is a function of x. What that means is we can apply the chain rule to y, just like we would any function of x. And I'll explain what that means as we work through this example here. Okay, so we have x squared plus y squared equals 25. Okay, so to proceed, we'll take the derivative d by dx of both sides here. And our goal is to solve for, so say, just to keep our eye on the ball here, goal, solve for dy dx, also known as y prime. Because I like to do these with y primes instead of dy dx's, because if you do them with too many dy dx's, it starts to get really cluttered really fast. So when I say y prime, I mean dy dx. And here's how we do it. So we know what d by dx of x squared is. That's simply 2x. That's just the power rule. Nothing new there. Whoops. Do that in black. So we have 2x, okay, plus 2y y prime equals derivative of 25 is 0. Now you're probably saying, why did you add in that y prime? Well, that's simply the chain rule. Remember, y was a function of x. So we had y of x squared here for this y squared. Well, when we take the derivative of that, it would be 2y of x times the derivative of the inside, that's the chain rule, y prime of x. So that's what's going on behind the scenes. Every time we take a derivative across a y term, but we're taking the derivative with respect to x, we're going to add on this y prime, right? And we'll do this over and over and over again. When you're taking the derivative of x stuff with respect to x, no need to add on the y prime, because we're not doing the chain rule. When we're taking the derivative of y stuff with respect to x, we tack on this y prime at the end, because really we're doing the chain rule, because whatever y is, it's some function of x. How do we know it's a function of x? Well, we solved it for x. Remember when we solved this whole thing for y and we got the square root stuff? Okay, that's all the calculus that's involved here, but now for the hard part, we need to solve for y prime. In this case, it's not so bad, but as you can imagine, as things seem to go in calculus, the algebra can become quite involved. So let's solve this thing for y prime. We can subtract the 2x from both sides and divide by 2y, so we get negative 2x over 2y, which is simply negative x over y. Okay, so there's the implicit version of our derivative. We're still interested in the derivative at this point 3, 4, because that will give us the exact slope of the tangent line. Let's see if it's the same. Well, indeed it is the same, right? We plug in 3 for x and 4 for y, we get negative 3/4. Same thing as before, which is what we would expect. Okay, so we're starting to get the hang of it. Let's try another example. Here we have y squared plus 3x equals 8, and we're asked to find dy dx. If you feel confident, or at least mildly confident, or even curious, feel free to pause the video and try this on your own, or we can just do it together here. Okay, so what do? We take the derivative d by dx of both sides. D by dx, and these will get more complicated, don't worry. Let's see, okay, so every time we take the derivative of a y term, we're going to tack on that y prime, and that's the chain rule because y is really a function of x. Every time we take the derivative across an x term, we just take the regular derivative. That is, when this bottom variable matches the variable, nothing special happens. When this bottom variable, this dx, is different than the variable we're taking the derivative to, you have to tack on that prime variable. Apply the chain rule every time. Okay, so this gives us 2y, y prime, there's our chain rule step, plus 3, derivative of 3x is 3, equals derivative of 8 is 0, since that's a constant. There we go, done with the calculus. Moving on to the algebra step, we're solving for y prime. So 2y, y prime equals negative 3, and solving that out gives y prime equals negative 3 over 2y. And that's our general derivative. And then of course we could plug in any x, y, I guess we only have y in this case, any y value along that curve to get the derivative specifically at that point.